Hey, how's it going? My name is Doug Wilklow. I am with Team Jackson here at software or here in yeah here in software engineering. Spring 2022. My team is Team Jackson. We are doing system design as our topic. So here is the divide for the work. Everybody's contributions to the PowerPoint, to the slides. I am the first section here, so I'll just dive right into it. So, what is design? Effectively, you are defining user requirements for a system so that it may be developed and implemented. This can be anything from user interface components to artistic design to functions. First off, we'll look at conceptual design, which is basically the early steps in a process as far as designing a product goes. It is basically the big picture. We're looking at the roadmap, um, very very large scope kind of idea, very broad strokes kind of design. Good, yeah, broad outlines of the system functions and user interface. A good example would be a user will be able to access their bank information through the app. So you're designing an app. It'll look like this, and the user will be able to do this with it. Now on to technical design. This is where we get into the nitty gritty. The more detailed description of how the project will meet the conceptual design. A good example of this would be going back to that bank app. The user inputs their username and password, where if it matches their user and pass in the SQL database, their associated info is pulled through to the app for use. Now, the programming or event team writes the code, implements the functionality. They are the ones who are going to be making the magic happen effectively. They're the ones who do the work of putting the code together. All right, on to the next slide. So, what is good conceptual design? Well, good conceptual design creates a very clear outline for what the product is meant to be. A good example of this would be concept art in general. It doesn't have to be on the right here. We have two images of a character from a video game called Team Fortress 2. It came out in I want to say 2006. But here is the early concept art on the left, the blue in the background. You can see he's like very wiry looking, that kind of thing. So the general concept for this character was already planned out and made, where he's supposed to be able to run fast and be hard to hit, that sort of thing. And that carried over into his final design here on the right. But that's generally the idea of concept art. This can be art for an app, like where the buttons are, where the UI elements are going to be, like graphs and stuff like that, where data is going to be shown to the user. Yeah, concept art and the cool idea you've had for an app. You should get on that. That joke didn't. All right, doesn't translate as well when there's not an audience. Anyway, for good technical design, this sort of thing it's back to the nitty gritty. Gives a good technical guideline for how the application should do what it's trying to do. So this is the SQL, like in the previous example, the SQL database would be the part of that implementation. Good examples of technical design would be UML diagrams, design documents, which basically break down what the classes and functions are for each variable, data structure, and object. And what the UML diagram does is it very handily shows and spreads out and lets people know what inherits from what takes properties from what, and what can access the variables of what. So decomposition. We're looking at I believe his name is Tony Wasserman's model for software architecture, which is effectively that different architectures can solve the same problem multiple different ways. Each version has its own pros and cons. So our idea is to factor problems into smaller issues by decomposition. Effectively, we're breaking a complex system into modules. These modules are each easier to understand than the previous. It can be broken into smaller modules if need be, if a problem is not small enough already. In order to solve the whole problem, solving each module individually will eventually get you to that goal. So that is it's a divide and conquer approach, if you will. So in order for this to be effective, each module must be well defined. that means providing as many details as possible. That includes variable names, functions, and data structures. So generally, any sort of implementation, any sort of thing you need for the implementation should be in the description of what this is doing here. So top-down design, breaking a problem down into smaller modules. These modules are either solved or broken down into smaller modules themselves to be solved when small enough, like I was saying before. Levels of design. We've got high level, which is the stuff at the top of that tree, that module tree, the decomposition. These describe a system or product in a big picture sense, much like the conceptual art and conceptual design that we were looking at earlier. These are functions that exchange inputs and outputs, a service that is a collection of features and conceptual data structures. So just like, oh, we should have it in a heap. And then low level is implementing that heap. It is providing details on how high-level designs should be implemented. It divides functions into sub-functions, possibly into more lower levels. So like functions into sub-functions, and then identify interactions between features. Details as to how the data structure can be built will be included in these modules. Or these low-level designs, I mean. In these low-level designs, the details will be included. So, a design issue, modularity and abstraction. For abstraction in particular, I can show off this graph here. This is the OSI, the Open Systems Interconnection Models right there. Basically, it goes around here and up through here. Starts off application, presentation, session, transport, network, data, physical. This is the different layers of abstraction that data goes through when being passed through the internet between computers. So we send a file to an application. It goes to the presentation layer, then the session layer, which is basically what connects you to a server and keeps you connected. Transport is how it moves. Network moves it, I believe, to your router. Data is where the router sends it to your computer. Physical is where it is in your computer. And oh wait, no. Data, I believe, is in your computer still. It doesn't matter. Either way, it's the different levels of abstraction as you're moving data from computer to computer. So effectively, the details of what the previous layers did are hidden from a current layer. Like if you are right here at network, down here at the left network, you can't see anything that happened above in the transport session presentation application. And as you go through each frame previous to this current frame you're looking at is in fact it's the way it got the data that it has is hidden, so that this layer, if it does come under some attack or is compromised in some way, then it doesn't leak the data or mess anything up really bad. It can't do that much damage. All right. Yeah, modular design enables very easy cleanup, very easy bug fixing, and just a general. It's just generally a good idea. So this one's a bit of a doozy, bit of a text wall for you. Apologies. Different types of architecture styles, pipes and filters. That is passing input data through pipes to a sequence of data transforming filters to produce output data. That is basically, it looks very similar to AND and OR gates, where essentially you are dealing with lines, like wires leading to boxes, where the box does some function, passes it through to some other wire, which passes it through to another box, and so on and so forth. Object-oriented design. By this point in our majors, we have all likely seen this, and built a project using this design method. This is treating classes in a system as objects which inherit traits from parent classes. So that's what the UML diagram I was talking about before. That's what that is generally for mapping that out in a technical way. Implicit invocation is when an event occurs at one component, a signal is published. There are several components elsewhere listening for this signal. When those components hear that signal, they react with their own procedure. So they set off or basically one sets off an alarm, and the others respond to it by doing some function. Layering is organizing a system into layers, like the OSI model. Each layer provides service to the one above and acts as a client to the one below. Repositories are basically made of two components: central data store and data accessing components. Shared data stockpiled in the data store. This is basically a system where it's kind of like a spider almost. Visually, if you imagine that, a big ball in the center, a bunch of legs poking out to further nodes in the ends that are trying to read and write the data. A big old pile of data right in the middle. A bunch of lines going out, branching out to these computers that are trying to use it. Interpreters. They execute commands without having to compile them into machine code. When I looked this up, it reminded me of Python, in that it just kind of does stuff without really thinking about it. Anyway, process control. A process stays within the bounds it's supposed to and delivers the expected result. That just means that if process control is in place, processors are doing what they're supposed to be doing, and they are delivering the expected result. All right, that is it for my section.
Going to discuss is design issues when it comes to modularity. So modularity, of course, is known as like separation of concerns, where concerns would be any aspect of the requirements or design that we want to define or understand in more detail. So that would include functions, data, features, or tasks or qualities. So it would be basically the principle of keeping separate the various unrelated aspects of a system, so that each aspect can be studied in isolation. So as we discussed before, decomposition, when building a modular design, we must decompose our system. So by identifying the system's unrelated concerns and encapsulating each in its own module, this will then, of course, break down the program if we're looking at it from a technical aspect, which then does raise concerns where there's disadvantages of there being where it will require extra time and memory when it comes to modularity. And also you have to think in the aspect of you have to be careful of the documentation when it affects each separate part of a program when there's when you're focused on each individual module as well. So this method will make it easy to understand each module and locate faults and make changes to the system without affecting everything. So bring a decent amount of flexibility with all the system components when working as a team on modular design. Now, so this is just a visual explanation of how modularity would work with two different applications. As you can see, like with each module, when we separate and focus on the individual design, then you can utilize that and implement to a different application, as you can see with module 1 and module 1 here. And then we're going to focus on collaborative design. So what is it? It's a team-based design as an approach that is becoming more popular, where different parts of the design are assigned to various people in the team. Collaborative design will help each individual grow as developers, as they're able to learn and improve upon certain skills areas that they may have been previously lacking in. So as great as collaborative design is, there do seem to be disadvantages that come along with it, certain issues that you have to consider. That's just these would be deciding who is best suited to design each aspect of the system. You have to discuss amongst the team, see who can handle what in the best case scenario, even though you want everybody to have clear communication and understanding. There's also how to document the design, so each individual team member is able to understand and work with the design of others. Again, communication is a big point for this. And then there's also how to coordinate the resulting software units so that everyone's work within the team will have no issues when integrated together. So here are the concerns that come with it. To be more specific, would be um, so you should also consider the different cultural and preferences that come with working with multiple individuals. So there's differences in personal experience and understanding their own personal preferences that come with programming or designing. There's also a possibility that any number of individuals within the team may have unique background and might come from different places where they learned how to work. It might differ from the culture that you grew up in. So, for example, there was a study in 1990 by Ishii where it was determined that Japanese software developers are less likely to express individual opinions when working in a group. And this is due to the understanding that they value teamwork more than individual work. So, and this was then further strengthened by another study in 1994, which basically proved that a Singaporean group valued harmony, which is basically when there's no conflict and there's junior personnel would of course defer to opinions of senior colleagues, which differed from an American group that valued parallel communication and anonymous information exchange. So there's more, I guess, conflict amongst the American groups. So there's different cultural backgrounds they have to consider when working in different teams. And there's also distributed development. So distributed development is when, as we can discussed earlier today, there's a financial aspect to this that we have to consider. In which industries, as they grow, they're going to want to cut costs and not waste too much money. So what they'll do to not what they'll do is outsource, which hopefully doesn't affect productivity in their companies. So due to this, a collaborative design team will be distributed around the world. So, and when it comes to distributed development, there's 4 stages that we should consider. First stage would be a project that is performed at a single site with on-site developers from foreign countries. A second stage would be an on-site analyst determine the system's requirements, which are provided to off-site groups of developers and programmers to continue development. A third stage would be the off-site developers build generic products and components that are used worldwide. And the fourth stage would be the off-site developers build products that take advantage of their individual area of expertise. So the issues that come from distributed development, of course, is um, when enhancing everyone's understanding of the system developed, this model will it brings up the problem of communication, as you see in the second stage, where there's basically the on-site analysts, they'll come up with requirements, and then there's not much communication between them and the off-site groups that are probably across the globe working on developing whatever the product may be. And of course, there's other small issues that could be like time zone differences, unstable internet connections, and there's also, as we discussed before, cultural things that you may have to consider with on-site analysts or developers, where they might not understand certain local business customs or laws that would eventually lead to certain contention amongst outsourced sub teams. And basically, to sum it all up with collaborative design is, as we discussed, communication difficulties that will happen constantly, which is when communicating within a distributed team, there are many tools to help each individual member clearly voice their opinions and ideas and concerns as they are across the globe. Of course, there was understanding where a human behavior study that basically there's the concept to take into account that there may be a great deal of information through gestures and facial expressions that may lead to miscommunication amongst team members. But now, as technology has increased and progressed with video conferencing tools, there's not that much of a major concern, but yet there may be certain lack of communication that occurs through emails or any other form of electronic communication. And of course, there's also to take into consideration a language barrier that must be considered when there's not a complete translation between two languages, with certain cultural aspects and nuances that come with it. So as there, you can understand another person that speaks a different language, but not fully. There may be a loss of translation a little bit, which could lead to certain issues. Um, so then there's also issues that we must consider when designing the user interface. So, of course, identifying the humans who will interact with the system, each client or individual that's going to require the interface, they might have certain preferences, and they may be a certain type of have a certain type of personality that you have to consider when developing. They could be very indecisive. They could be very strict on certain things that they want. So you have to take that into consideration. Um, Defining scenarios for each way that the system can perform a task, of course. Designing a hierarchy of user commands and refining the sequence of user interactions with the system. Designing relevant classes and hierarchy to implement the user interface design decisions. And of course, integrating the user interface classes into the overall system class hierarchy. So these are all things to consider when developing a user interface and certain issues that you may run along that you'll have to work on.
Mhm.
And of course, we should focus on the design issues when it comes to concurrency. So concurrency is in software engineering would mean the collection of techniques and mechanisms that enable a computer program to perform several different tasks simultaneously. So of course, there's certain control techniques that concurrency contains that would be two-phase locking protocol, um, timestamp order protocol, multi-version concurrency control. So these are all certain techniques that will help develop concurrency and making sure everything works simultaneously. And synchronization, of course, goes along with concurrency. So, what are some problems presented with concurrency? Would be it would be required to protect multiple applications from one another. It can lead to lack of performance when running too many applications concurrently. And of course, we wouldn't want that when working on certain programs. Of course, there would be race conditions and blocking, starvation, and deadlock, which are all issues um, that come along with concurrency. And of course, race conditions can be solved with mutual exclusion. So when, of course, race condition occurs of the outcome, which depends on like which like processes get to be completed first. So mutual exclusion would work on that, but there are problems that come along with that, such as it would only work with a single computer system, or but it would be difficult to work with when it comes to a distributed system.
All right, now we're going to talk about component dependence. First, we're going to talk about coupling. This is defined as a measure of interdependence among multiple modules. This is how modules interact with one another by using shared data to perform a desired functionality. The goal of coupling is to keep the degree of coupling as low as possible. There's different forms of coupling. We have tightly coupled. This is where one module is a reference from another. An example of that would be where module A controls module B by sending a flag to give status updates of a subsystem. Then we have loosely coupled. This is where data is being passed between modules. An example of that would be module A needs module B to perform some task using that data. And then we have uncoupled, where two modules are independent of one another. At the bottom, we have an image of loosely coupled and tightly coupled, kind of showing the relationship between each module. So loosely coupled to the left doesn't have that many arrows. Some modules are indirectly connected. Some are connected backwards and forwards. So it's loosely coupled, and tightly coupled is pretty much arrows connecting in every direction to each module. So they pretty much all have a relationship and a dependency on one another. Now we're talking about the different types of coupling. To the right, you can see an image going from uncoupled to content coupling. This basically goes from the most desirable to least desirable as you move up the arrow. So we're going to start with the most desirable, which would be data coupling. So passing of data values between modules. It's the easiest to trace data and make changes to the module. And we have stamp coupling. This is the passing of complex data structures between modules. The modules need to agree on the data format and organization. So you can imagine if you have the passing of a hash map, it needs to know that it is a hash map, so it knows how to work with that data. We have control coupling. This is where a module passes parameters or return values to control behavior of another module. So this makes it impossible for the controlled module to function without the direction from the controlling module. Next, we have common coupling. This is where data is accessible from a common data store. Changing data needs to consider all the modules access that respective data store. So to the bottom right, you can see a common data store and the box at the top of that image. There's globals and variables, and then you have the three modules below, X, Y, and Z, and they're working with that global data store. So they both, if the data store changed, they all need to know that it's, if it's an integer, a string, or what have you, so they all know how to work with the data properly. And then we have content coupling. This is a complete dependency on one another, tightly coupled, and cannot be designed or modified independently. And to the left there, you can see module B generates module D and then calls module D. So module D is completely dependent on module B. Without module B creating module D, it doesn't exist. So that's an example of tightly coupling. Now we're going to move to the next slide. Now we're going to talk about cohesion. This is similar to coupling, but where coupling is talking about the connectivity of each module. This is referencing the dependence within and among the module's internal elements. So this is looking internally on how all the attributes relate to each other. So a highly cohesive module have closely related pieces to each other and to a module's singular purpose. Why is this important? Multiple purpose modules is a higher risk of elements needing to evolve over time and at different rates. So can make it more error prone. And then what's the goal here with cohesion? It's to maintain a high level of cohesion so each module is easier to understand and resilient to change in design. And to the right, you can see we go from coincidental to informational. Coincidental being the least desirable and informational and functional being the more desirable models of cohesion. Move to the next slide and go over these. Beginning with the least desirable form of cohesion would be coincidental. So where modules parts are unrelated to one another, usually due to some sort of convenience. You can imagine early development stages, you have a module that's kind of a miscellaneous module where a bunch of functionalities are thrown into one module and they don't necessarily make sense with each other. This isn't really good for the longevity of the project. So yeah, that's basically what coincidental is. Now we move to logical. The parts are related only by the logic structure of its code. It's difficult to understand and maintain as operations evolve over its life cycle. There's actually an image over there to the right where it kind of shows how that works. You basically have two different functionalities that perform the same code at the end. So you have an if and an else that, depending on what it needs to do, it's going to perform those tasks and then compute something after those if statements are complete. Then we have temporal. This is where modules, data, and functions are related because they are used at the same time in an execution. This often leads to duplicate code where multiple modules perform similar operations on key data structures. Then we have procedural. So where functions are grouped together in a module to encapsulate order of execution. So similar to temporal cohesion, but the functions pertain to a related action or purpose. I'm going to continue from here. We have communicational. This is where a module is designed around a data set. A group of functions and have a relationship is based on operation in shared data set. An example of that is an input sensor. So you can imagine you have an input sensor that returns a bunch of data that needs to be worked on by the software. So there's a module that works directly with this input sensor and captures all that data. And then other modules would communicate with that module to actually extract that data. And then the most desirable, we have functional. This is the ideal method where it performs only the functions of which it was designed. So it has a singular purpose. Then informational, this is similar. to functional, where it says this is an adaptation of functional cohesion to data abstraction in object-based design. So put data, action, or objects together when they have one common sensible purpose. All attributes, methods, actions are strongly independent and essential to the object. So informational is similar to functional, and informational is more object-oriented, design-based. We'll move on from here. Now we're going to go over an example that kind of shows this cohesion at work. So this is based off of an example in the textbook. It's keyword and context quick. And how this operates isn't all that important for what we're interested in, but just to give some context, basically it takes input as an ordered set of lines, which are an ordered set of words, which is an ordered set of characters. It performs a circular shift to the first word and appends it to the end of the line. And the output is all the resulting lines in alphabetical order. So to the left there, you can see that you have a master controller making these subsystem or subprogram calls for input, output, circular shifting, and an alphabetizer. And those solid line arrows are the memory access for data. So this is an example of sharing data. Everything's kind of pointing to the data that it needs. It's good for quick access to data, but not necessarily good for cohesion. And then the next one is showing how we're passing data. So alphabetizer is actually passing data index, which is then passing data to text, and kind of that relationship is a little more desirable over sharing data. It kind of filters data through as it goes along. The next example uses ADT, so an abstract data type, classes. It's similar to the last example, but it shows a little better version of abstraction, a little more desirable. And then we have the pipe and filter solution. This solution is really good. It pushes the data through each module and kind of filters it as it goes along. It's really simple, easy to implement, but not necessarily good for sharing data or passing of data. And at the bottom there, you can see a table how it kind of breaks down these modules and which is more desirable. So the attributes that we're interested in is easy to change algorithm, easy to change data representation, easy to add functionality, good performance, efficient data representation, and easy to reuse. So as you can see, there's a priority level there. These are matrixed with each score and kind of gives an output of what the overall score of each one is. So the first one we looked at was shared data, and it kind of came out the lowest, definitely the least desirable version to use. And then we have data abstraction. This was the second example, where kind of used modules to push data through each segment. So you can kind of see this gets a 69, which is pretty good, quite an improvement over shared data. And then implicit invocation. This is the third example up at the top left there. This uses classes. So this is another improvement over the second example, similar version of data abstraction, but using classes. And then you have pipe and filter. This one's pretty interesting because it didn't scored third highest, but it actually got fives in a lot of the areas except for data. So you could see it actually is really good, minus the data, how it uses data. And there's actually another example where it shows how you can combine some of these models to improve upon these. So you can imagine using implicit invocation and pipe and filter. If you can kind of combine those and get the simplicity by using classes, also using classes, you can further improve on this cohesion. Now we're going to talk about exception handling. So exceptions are things that are undesirable outcomes of programming that need to be addressed when we run into issues and recovered from. So what is exception handling? This is where a system addresses each exception in a satisfactory way and returns the system to an acceptable state. The goal is to maintain reliability and robustness. In order to maintain this, we must correctly perform required functionality under the assumed conditions and function correctly in presence of invalid input or stressful conditions. Some of the typical exceptions that we run into are failing to provide some service, providing the wrong service, corrupting data, violating system invariants such as security protocol, or deadlocking. So now that we've discussed what an exception is, we kind of need to know how to handle them. So some things we can do is undoing transactions, we can have checkpoints and rollbacks, have backups. We can degrade service, correct and continue, or reporting. And an example of that is below. You can see a temp transmission that accepts a message as a string. It raises a exception called transmission exception. And what this program or this piece of code does is once it reaches 100 unsuccessful transmissions, it will throw an exception so that it can be handled or prompted to the user. So you can see there's a local failure set as an integer. This is our counter variable. It's going to try to transmit an unsafe transmit with this message as a parameter. And if that fails, it goes to this basically rescue function, which would be our try catch in C++. Increments failure. If this failure reaches 100, then it throws an error. Otherwise, it retries. So yeah, we basically want to catch these exceptions before they bubble out of the environment. Maybe we can recover from them, using maybe a correct and continue, but maybe we can't, so we just report it. So that's an example of how you can handle an exception. And now we're going to switch gears to control issues. We're going to talk about a scope of effect. This is where a module is affected by a decision made by their respective module. So essentially, the hierarchy of modules and how they relate to each other. So the scope of effect for a module must lie within its scope of control. A module itself and all of its subordinates are within its scope of control. So looking at an example, at the bottom left, you can see an example of a program that basically takes a credit score and decides if they are able to get a short-term or long-term loan. And you can see a decision down there at the bottom left where based on the credit rating, they're going to set their term as long or short. And the effect of this decision is actually outside of its scope of control. It's up a level where processing a short-term loan should be in its scope of control. So at the right there, you can kind of see how it adjusts that and moves that decision within its scope. It makes more sense for the design of the program. So yeah, you don't want a module kind of reaching in other parts of the program where it doesn't really make sense and can have negative side effects that maybe weren't foreseen. Now we're going to move to scope of component. This is where attributes, methods, and actions are strongly independent and essential to the object. Supports modularity and knows nothing about implementation of its object-based attributes and can manipulate these attributes only by using their interfaces. So a good example of this is, classes and objects. You have a car class that creates these different objects. Those are red, blue, and green cars. They're Ford, Toyota, Volkswagen, different models of those vehicles. And these objects are only working with this class through its interface, so it's structured in a way that doesn't allow these objects to manipulate the data other than what was intended. So the scope of components essentially that all the pieces within this these objects are related, and they can't really be manipulated in a way that doesn't make sense. So you wouldn't put that, this car is also a truck because this is a car class. It's not a vehicle class. A vehicle class, maybe would be something that would allow trucks or buses or cars and so on.
Fault tree analysis. This is a technique developed to help us analyze the design and look for faults that might lead to failure. A fault tree traces backwards through a design along the logical path from effect to cause, hence helping us decide which faults to correct or avoid and which faults to tolerate. To analyze, we identify possible failures. Although our identification takes place during design, we consider failures that might be affected by design, operation, or even maintenance. We can use a set of guide words to help us understand how the systems might deviate from the intended behavior. Next, we build an upside-down tree whose root node is some failure that we want to analyze and whose other nodes are events or faults that realize or lead to that root node's failure. The edge of the graph indicates the relation among the nodes. The parent nodes are drawn as logical gate operators and an AND gate if both the child nodes event must occur for the parent node to occur, or an OR gate if one of the two child node events must occur for the parent node to occur. Sometimes an edge is labeled N of M if the system includes M redundant components. where n faulty components lead to the designated failure. Each node represents an independent event, otherwise, the analysis must be invalid, especially with respect to compound faults. As we can see in the given diagram on the slide, for an illegal access to be granted, both the password must be exposed and the password should not have changed. Hence, an AND gate is used to connect the child and the parent nodes. Similarly, for a security breach to take place, either an illegal access must be granted or a previous logout should not be recognized, hence connecting the child node to the parent node using an OR gate. Mathematical validation. A mathematical validation is defined as the process of determining the degree to which a computer model is an accurate representation of the real world for the perspective of the intended model applications. Mathematical validation can be done by making various types of models. Models that are central to the design because we must be able to predict the behavior of the devices or the systems that we are designing. Measuring design quality. Design information can be used to predict which part of the software are most likely to be problematic. We can take steps during the design stage to build in fault prevention or fault tolerance, and we can focus more on the initial testing efforts on the most fault prone parts of the design. We use the method by Brian Murasco and Basili approach to measure design quality that has three different characteristics: the relationship between classes, the types of interactions between classes, and the loci of ripple effect due to design changes. For example, the report that when a class depends on a large number of attributes that belong to another class that were not ancestors, descendants, or friends of that class, then the resulting code was more fault prone than usual. Similarly, when many methods belong to a friend class depended on the methods of a particular class, then that class was more fault prone. In this way, the design information can be used to predict which part of the software is most likely to be problematic. Now comparing designs. Comparing designs is very important since there can be multiple designs for a single project idea. So there are usually multiple designs, and it is important to choose the most efficient design that fulfills the majority of the client's requirements. And hence we need a measurement based method to compare these designs so we make an informed decision. We can compare these designs using comparison tables and cost benefit analysis. We can see how a comparison table lists the attributes and marks the four different designs and how they either satisfy or don't satisfy the attributes. This makes it easy to choose a design looking for a given table. However, we can't just take a decision based on these attributes. We need to consider the priority of these attributes to take a well-informed decision. Here, we could choose the implicit vocational design, which is the first table on the screen. Now, these priorities and ratings, as well as the choice of the attributes, are subjective and depend on the needs of the customer and the user, as well as the preferences for building and maintaining a system. Most companies define effectiveness of a system in terms of the value of cost. How much value will it propose change and add to the system compared to how much it would cost to implement that change? A cost benefit analysis is a widely used business tool for estimating and comparing the cost and benefits of a proposed change. Here we analyze the return on investment and which design gives us the highest return on investment. Design review. It is an essential part of the engineering practice, and we evaluate the quality of a software architecture document, also known as SAD, in two different ways. We validate the design to make sure that we are building what the customer wants, and we verify our documentation to help ensure that the developers will be productive in their development tasks. SAT serves as a repository for information about the architectural design and helps us communicate this vision to the various members of the development team. The SAT should include a system overview, views, software units, analysis data and result, design rationale and definitions along with the glossary and acronyms if used in the document. To evaluate the quality of a SAT, we use two different ways. First, we make sure that the design satisfies all the required specifications of the customer. This process is known as validating the design. We then address the quality of the design. Verification involves ensuring that the design adheres to good design principles and that the design document fits the need of the user. As mentioned earlier, we validate the design to make sure that we are building what the customer wants. During validation, we make sure that all aspects of the requirement are addressed by our design. To do that, we invite several key people to review it, like the analyst who help to define the system requirements, the system architect, the program designer for this project, a system tester, a system maintainer, moderator, recorder, and other system developers that are not otherwise involved in this project. However, we must keep in mind that the number of people taking part in the review depend on the complexity of the project, and the total number should be kept small so that discussion and decision making are not hampered. We then verify our documents to help ensure that the developers will be productive in their development task. To do that, we examine the design to judge whether it adheres to good design principles. Is the architecture modular, well structured, and easy to understand? Can we improve the structure and understandability of the architecture? Is the architecture portable to other platforms? Is the aspect of the architecture reusable? Does the architecture support ease of testing? Does the architecture maximize performance where appropriate? Does the architecture incorporate appropriate techniques for handling faults and preventing failures? Can the architecture accommodate all the expected design changes and extensions that we have been documenting? And these furthermore questions help us verify correctly whether the architecture is as required and desired. An active design review is a particularly effective method for evaluating the quality of SAD and validating it. In an active review, reviewers exercise the design document by using it in ways that developers will use in the final document in practice. This is, rather than reading the document and looking for problems, which is characterized as passive review process, the reviewers are given or devised questions that they must answer by looking up information in the SAD. Each reviewer represents a different class of reader and is asked questions suitable for his or her use of the SAD. Thus, a maintainer may be asked to determine which software units would be affected by an expected change to the system, whereas a program designer may be asked to explain why an interface preconditions are necessary. Now, passing it on to Dorian.
Okay, let's talk about design examples. Software architectural styles are established large-scale patterns of system structure. Like architectural styles for buildings, software architectural styles have defining rules, elements, and techniques. These techniques result in designs with recognizable structures and well-understood properties. Styles are not complete detailed solutions, however. They are loose templates that offer distinct solutions for coordinating a system's components. Architectural styles focus on the different ways that components might communicate, synchronize, and share data with one another. In the early stages of software development, architectural styles can be useful for exploring and exploiting known approaches to organizing and coordinating access to data and functionality. By constraining intercomponent interactions, architectural styles can be used to help the resulting system achieve specific system properties, such as data security can be achieved by restricting data flow, and maintainability can be achieved by simplifying communication interfaces. Software architectures are rarely based on a single style. Software architecture is built by two following things: combining different architectural styles and selecting and adapting aspects of styles to solve particular problems in the design. Architectural styles can be combined in different ways, though. Different styles might be used at different levels of system decomposition. For example, system's overall structure might be viewed as a client-server architecture, but the server component can be subsequently decomposed into a series of layers. Specifically with this, one architecture's publish-subscribe interactions can be decomposed to elaborate the components and protocols used to manage event subscriptions and to notify subscribers of event announcements. If an architecture is expressed as a collection of models, how the documents relate to one another must be documented. If one model shows the decomposition of an element from a more abstract model, the relationship is straightforward. If the two models show different views of the system and there is no obvious mapping between the two views' software units, then documenting the views' correspondence becomes more important. And recording the correspondence was talked about earlier with the software architecture design. The SAD details how to correctly document the correspondence. Again, architectural styles can be combined in different ways. An architecture may use a mixture of architectural styles to model different components or different types of interactions among components. Integration of different architectural styles is easier if the styles are compatible. All the styles being combined might relate runtime components or code units, or different views of the architectures can be created and maintained as building architects do. For example, there's an electrical wiring view, there's a plumbing view, and a heating and air conditioning view, and this all helps the architects focus on what is important in their plan. This approach, specifically integration, is appropriate if integrating the views would result in an overly complex model. When components interact with each other and multiple views, for example, again, mapping between the views components is messy, many-to-many relationship, integration would be the way to go. So a picture here. In this example, several client components interact with each other using publish-subscribe communications. The publish-subscribe communications are the little two vertical, two horizontal line type thing at the top. These same components use server communications via request/reply protocols. Those are the thinner arrows. In turn, the server components interact with a shared data repository. In this example, the architecture integrates different styles into a single model by allowing components to play multiple roles. Again, example, client, publisher, and subscriber, and to engage in multiple types of interactions.
All right. So for this part of our presentation, we're going to be going over what was titled the SE Lab, specifically focusing on a couple of examples of design failures and some evaluations of those design failures, talking about things that have been talked about throughout this presentation. And I thought that this quote was pretty poignant by Stuart Firestein. And that evaluating failures and evaluating where we went wrong is as important, if not more important, than evaluating what went right. So the first one would be actually the first one that is given in the text, and a pretty classic example of design failure and oversight done wrong. So this is Ariane 501. This is an unmanned flight from the ESA, the European Space Agency. This is about the mid-90s, and they had been doing a lot of tests, a lot of development for about a decade to get this ship going. Approximately $7 billion in development and $500 million in raw costs just to get this flight going, including everything in the cargo bay, the rocket, the fuel, all proceedings. It gets about halfway to orbit before, like you can see in the picture, it erupts and explodes violently in the air, demolishing all the cargo inside and having all this debris rocket towards the ground about halfway to orbit. So why did this happen? Thankfully, nobody was harmed. Obviously, it was an unmanned mission, but how did we get $7 billion of damages in what was about 30 seconds? Internal Board of Review found that it was 100% software related. An inertial engine was calculating the horizontal velocity to the ground platform as it starts to waver off towards orbit, because you never take a direct shot. So we need to keep track of horizontal velocity relative to the ground. However, the number used initially on the calculation was a 64-bit floating point, and the calculated number would be sent to this inertial, basically autopilot, to determine how we need to adjust our trajectory. So this 64-bit would be sent to this inertial engine, but this inertial engine only read in 16-bit integers. So it would cap out at 32,767. The failsafe, the fault detection, the fault detection, in this case was not to evaluate and recalculate as we've talked before, but it was instead just to shut everything down. If we hit errors, it was just a cold stop. And of course, when you have a system that is designed to calculate horizontal velocity and to determine when these engines have to go, having them full stop means that a lot of the ship's components will also full stop. According to the ESA, this caused complete loss of guidance and altitude information 37 seconds after start of the main engine ignition. Also 30 seconds after liftoff, basically. So the ship was airborne for all of 30 seconds. NASA's approach to hardware, having what they call a hot standby, they've used for a pretty long while, and this worked for a long while when software was very rudimentary and a lot of their tech was hardware focused. Having things on hot standby as in redundancies, so we'd have not one engine but two engines, and they would be pretty much the exact same. In the case that one engine fails, we just switch to the second one, and usually what was wrong with the first one will be solved by the second one. If there is some issue, it's usually some defect or some individual minor implication that swapping to the other engine would fix. They applied this design overview to software as well, and obviously this does not work well in software, because if you have an error in hardware, there's a very good chance that it could just be specific to that one piece of hardware. Some thermal paste not in the right place, some alloys are falling apart, something's not bolted on right, but it's probably fixed in the duplicate. Software, if there's an error in the first one, there's most likely the same error in the second one. What can we learn from the Ariane 501 disaster? Client-side components need to have context for recovery and exception handling. Like we talked about before, the exception handling was to shut down after these exceptions, like integers being way too big, were logged. And while this worked well, this exception handling worked well for lesser systems, non-crucial systems, in which a fresh reboot usually would fix the issue. Especially in what the ESA was talking about was the back-end software, back-end testing. Rebooting would fix a lot of these issues. Things that are mission critical, like determining engine velocity relative to the horizontal position of a platform, cannot be rebooted. There's not enough time. In the review, the internal board said that working with the maximum value or attempting to work around this error could have kept it running long enough for the rocket to achieve orbit, even if not efficiently. Just anything to keep it from twirling into the air and exploding on itself. Another thing is, again, like we talked about before, these hot standby systems work really well for physical systems, but not for software design. In an evaluation at the time, 2004, of NASA software failure causes, most of these errors logged would be things like logical errors, things that would be internal to the software and would be easily replicated onto all other softwares. It usually wasn't a cause that was individual to the software. Besides, I think they listed gamma radiation, and I'm not a radiologist, but I'd assume that gamma radiation would affect different copies of software differently if there's bit flipping. But besides that, most errors that they had would be innate to all copies of that software. It wouldn't be in an individual case. This same overflow issue, this converting a 64-bit floating point to a 16-bit signed int, cropped up a lot of places in the software. So not only was it the inertial calculations, but a lot of other smaller systems also failed. And it was accumulation of all these systems. So that's why things like architectural reviews, design reviews, like talked about earlier in this presentation, and error testing are necessary to avoid compounding redundant errors. So for another example, this time on the ground instead of space, let's talk about the Tacoma Narrows Bridge. It was built across Puget Sound in the 40s in Tacoma, Washington. At the time, it was the largest suspension bridge ever constructed. Bridge engineers had been designing smaller suspension bridges for a long time, and these held up super well. They looked very beautiful, just because you were able to eliminate trusses, and Washington State wanted something, that looked pretty. So the design standpoint for these engineers was to take existing bridges and simply scale them up instead of redesigning suspension bridges. The thought process was, hey, well, obviously it's worked thousands of times across smaller suspension bridges. Why would it be any different for a bridge just a little bit larger? So the problem was, so when you build a bridge, trusses are, if you can imagine, those triangle-looking steel beams that usually sit above a bridge to keep it structurally sound. Smaller suspension bridges would often omit these simply because the suspensions themselves would be sufficient, and they were small, so things like inclement weather would not affect them enough. However, when they scaled it up, they did the same thing. They omitted these trusses. They wanted it to look better. They wanted it to look cleaner, and they said, well, it seems that these trusses aren't necessary in a suspension bridge, because in these smaller suspension bridges, we can do without them. So the suspension themselves must be able to hold up the bridge. And they were right. The bridge held up under normal conditions. The bridge would hold up under regular car driving. However, while it held under the pressure of the cars pushing down, did not have the same benefit from a truss as in keeping it from twisting, keeping it from bending. So at high winds, this bridge would twist. In this bottom right image, you can see this bridge start to warp left and right. And super inclement winds during the winter of that year caused this bridge to warp enough to the point where it basically snapped at the middle. The supports can no longer trust it, and it crumbled, reported to actually just crumble at each end, falling into the river below. Estimated to cost about $6 million at the time, which, adjusting for inflation, is over $1 billion today. And that bridge has since been completely swept, besides the bits that crumbled. And interestingly enough, the bits that crumbled into the Puget Sound below are currently giant reefs. Coral and sea life now live in those pieces. They haven't been excavated out of the Puget Sound. It's actually some of the biggest reefs in the area come from the remains of this bridge. So I guess $1 billion reef, inadvertent or not is nice. But this bridge lasted a little only over 4 months. So, what can we learn from this? What can we learn from the $1 billion 4-month bridge? It is not enough for a system to be reliable. It must also be robust. And we have to get a good understanding of what both of these things mean. And the hope is that after my teammates have kind of done all their presentation, that we understand what the difference is between reliability and robustness. Reliability meaning that it works under ideal circumstances. Robust means if things go wrong, we can still we can still not function ideally, but we can still exist. We don't have an Area 501 problem where it just completely fails. It handles errors. So, Tacoma Bridge was reliable. On a normal day, ideal conditions, cars can drive perfectly. This thing held up for 4 months, and the thing that tore it down was not cars driving, not what it was intended for. Robustness, however, under less than ideal conditions, these less than ideal conditions cause the whole bridge to fall apart. The stressors cause the whole bridge to crumble, warp, and tear at the seams. Resilience is not only good for business and quality of product, but also can be life-saving. Obviously, resilience is good for a product because it shows quality in a product if it upholds under these stresses, under these weaknesses, under these attacks. Good for business, obviously, because we want our systems to be secure. But in this case, it was not only that. It was not only a financial concern, but it was a safety concern. If there was any way for this bridge to recover from things like inclement weather, if there was any backup systems at all, because if you can see, all that we have are these suspensions. We don't have any backups. There's nothing underneath the bridge. There's no trusses. We could have avoided a total collapse. We could have avoided human life being taken. We could have avoided a total bridge falling into the Puget Sound. Perhaps the system would still be broken, but at the very least, a safety concern for resilience. Results. Talking what actually happened in 1940, these results actually resulted in wind testing bridges. For a long time, wind tunnel testing, testing of the bridge conditions under high wind, was largely an optional test and often was omitted because of financial reasons. It's a good place to cut costs because these tests are expensive. However, this Puget Sound disaster, this Tacoma Narrows Bridge, showed that these tests, even though they're expensive and they're necessary for a good reason. We need to make sure that even under conditions like inclement weather, the bridge is robust. We reinstated heavy truss designs. These pure suspensions went away for a long time. It was only until recent developments, recent-ish, the late 1900s, that we were able to get rid of these truss designs because we have other designs such as under bridge supports. Similar suspension bridges, as in similar size at the time, all went back reinforced with steel trusses. They did not want to take the chance. They did not want to see what would happen if wind hit theirs like it hit the Tacoma Narrows. So this basically, the biggest thing that I think the world learned from the 1940s is that testing, even though it's expensive and even though it seems like it's pointless, is necessary. Having these design review sessions is not an optional thing. So that is the presentation. So thank you.